Here we have the definition of the natural log function, and the natural log of x is defined as the integral from 1 to x of 1 over t. And so this is no longer, this is a function, and it depends on x, and so it's not a fixed number, it's not just a value, but it changes depending on x. And so the natural log of x is defined as the area from 1 to x of the function 1 over t. And now let's look at the graph of the function 1 over t, and then also look at the area represented by this integral right here. So here we have the function 1 over t, and the area and so the log of 1.1 would be the integral from 1 to 1.1 of 1 over t. And this area right here, this area is 0.09531. And then if we go to 1.2, then the natural log of 1.2 is defined as the integral from 1 to 1.2 of the function 1 over t. And so this area right here is 0.1823. And then this is ln of 1.3, which is the area from 1 to 1.3. And this 1.4, 1.5, 1.6, 1.7, and so on. And then for area before 1, and so this is the area from 0.9 to 1. Then recorded if we switch the upper limit of integration and the lower limit of integration, then we have to put a minus sign in the front. And so this would be the same as this. And so if we switch the limits of integration, then we have to have a minus in the front. And so that's why it's equal to negative 0.110536051. And so the area from 0 to 1 is defined as a negative area with this function right here. And so ln of 0, natural log of 0.9 would be negative 0.1053. And then this is the area from 0.8 to 1, and it's defined as negative 0.223, the natural log of 0.8. And this function natural log here, it's only defined for x greater than 0. And so if x is 0, then the natural log function is undefined. If x is negative, this function is also undefined. And so to summarize it, the natural log from 0 to 1 would represent a negative area, and then greater than 1, then we will get a positive area. So right now this area here is 0.1 to 1, and the value of it according to this definition of natural log at negative 2.3025. So now the area is beyond 1, so that's why the value is positive. And so that's the definition of the natural log function. And so once again, natural log of x is defined as the integral of 1 over t from 1 to x. And so now what we like to do is find the derivative of ln of x of the natural log function. And so we want to show that the derivative of ln of x, or the natural log of x, is 1 over x. And so first, let f of t, the big F, be the antiderivative of the function 1 over t. So this is the function 1 over t, and then we'll let the big F be the antiderivative. And so by the fundamental theorem of calculus, this integral right here is the antiderivative, evaluated at x, the upper limit of integration, and then minus the antiderivative at 1, the lower limit of the integration. And so now we'll take the derivative of both sides, and so we have the derivative ln of x, which is the derivative of this integral right here. And so we have the derivative of the right side. And so this is the derivative, the difference, it's just difference of derivatives. And so we do the derivative f of x, which is f prime of x. But f1 is just a constant. This is just the derivative evaluated, the antiderivative evaluated at 1. And so this is a constant. And so the derivative of a constant is just 0. And so we end up with the derivative of the antiderivative. But the derivative of the antiderivative is the function f of x. F of t is 1 over t, therefore f of x is 1 over x. And so we have just shown that the derivative of the function, the natural log function ln of x, is 1 over x. And then the extension of this, if we have something like the derivative of ln of 8x, ln of bx, with a constant times x, and then we have to use the chain rule. So the chain rule would be, let's see, the derivative of 1 of ln of x is 1 over x. So the chain rule here, the derivative of bx would be 1 over bx, and then times the derivative of bx. B is just a constant here. And so we get 1 over bx, and then times b. Which is 1 over x. And we'll need this result in a few minutes. We have just shown that the derivative of 1 of ln of x, the natural log of x, is 1 over x, and then we have also shown that the derivative of ln of bx is 1 over x. And now what we like to show is that the derivative of the natural log of a product, x times y, is the same as the natural log of x plus the natural log of y. And so we have shown these two things right here. We've just shown that the derivative of ln of x and the derivative ln of bx are the same. So this is equal to 1 over x, and then the derivative ln of bx, they are the same. And so ln of x and ln of x, ln of bx, they have the same derivative, which is 1 over x, and so they must differ by a constant c. So for example, if we have a function like x squared and then another function like x squared plus 2, then the difference is just the 2. They both have the same, so let's write this down. If we have a function like, let's say, x squared, then the derivative will be 2x. And then if we do the derivative of x squared plus some constant, then the derivative here be just also 2x. And so the difference is by the constant c. So that's what we mean when we say, so they differ by a constant. And so if two functions have the same derivative, then they must differ by a constant c. And so what that means is that the difference ln x, ln bx minus ln x is equal to some constant c. And the orders, it doesn't matter which order we put, whether it's ln x or minus ln bx or ln bx minus ln x, it doesn't matter. And so now we have the equation ln bx minus ln x equal to c. And so we want to know what is c. And so we let x be 1, then we get ln of b times 1 minus ln 1 is equal to c. But ln of 1 is the area of the integral from 1 to 1, which is 0. And so no, ln 1, this is the area from 1 to 1 of 1 over t dt. But the area from 1 to 1 is 0. And so this will be 0, and so we have ln of b minus 0 is equal to c. And so c, the constant, must equal to the natural log of b. And so now this is the equation that we had earlier, this equation right here. And so c now is ln of b, and then if we add ln x to both sides, then we'll end up with ln bx is equal to ln b plus ln x. And now if we substitute y for b, then we get ln of x times y is ln x plus ln y. And next, we like to show that the natural log of x to the r is just some rational number. It's the same as the rational number times the ln x. So the derivative of ln of xr by the chain rule, it'd be 1 over xr times the derivative of x to the r. And then this is just x with some power r. So by the power rule, the derivative x to the r is just r times x to the r minus 1. And so now we have 1 over x to the r, and then this is the same as r times x to the r times x to the negative 1. Recall that for something like this, to combine, we just add the exponent. And so x to the r minus 1 is just x to the r times x to the minus 1. But this x to the r will cancel out with this x to the r. And then x to the negative 1 is the same as 1 over x. So once again, this x to the r and this x to the r, this and this, they will cancel out. So what's left is just r times 1 over x. So we've just shown that the derivative of x to the r is r times 1 over x. And now let's look at the derivative, the right-hand side. R is just a constant. So the derivative of a constant times the function ln x is the same. Because this is a multiplication constant, we can place it, we can move it out and place it in the front. And so this is the same as r times the derivative of ln x. But the derivative of ln x is 1 over x. And so we have shown that the derivative, the left-hand side, and the derivative, the right-hand side, they are the same. And so since the derivative of ln x to the r and r times ln x, the derivative the same, then their difference must be, they must differ by a constant, and we'll call it c. And so we end up with the equation x, ln x to the r minus r times ln x is equal to the constant. So we want to know what is this constant. And so if we let x be 1, then we get ln of 1 to the r minus r times ln 1. 1 to the r is just 1, but ln of 1 is just 0. Because ln of 1 is the area from 1 to 1, which is 0. So this is 0, and therefore c must be 0. And so this equation right here now becomes ln of x to the r minus r times ln x is equal to 0. And therefore ln of x to the r is the same as r times ln x. And so this is called the power rule. For natural log. And then we have one more, which is the quotient rule. And this is called the quotient rule. And so we like to show that the natural log of x divided by y is the same as ln x minus ln y. And so this is x divided by y. We rewrite it as x times 1 over y. And so now we have ln, the natural log of a product. And we have just found that natural log of a product is the same as the sum of the natural logs. So this is the same as ln of x plus ln of 1 over y. But 1 over y is the same as y to the negative 1. And then we have just shown the power rule. Ln of 1, y to the negative 1 is the same as negative 1 times ln of y by the power rule. And so we end up with ln of x minus ln of y, 1 ln of y. And so this is equal to ln x minus ln y. Once again, this is called the quotient rule.